Good morning, everyone, and welcome to the Virtual Festival of Geology live event schedule, and in particular the lecture series. It's good to see so many of you here. At the moment, we have 89 people present. And without wasting too much time, I'd just like to let you know that you have two hosts in the room this morning. Myself, I'm the chair of the Geologists Association, Vanessa Banks, and also Professor Tony Doré, who is supporting me just in case we have an issue with connectivity or anything like that. Professor Doré is on the council, and he is a petroleum geologist, and will be happy to help with the question session should I drop out for any reason. So with no more ado, I'd like to welcome Emma Liu, who is giving the first of the talks. Emma is a lecturer at University College London. She was a Leverhulme Early Career Research Fellow, which is an accolade, in volcanology, and her current research project is titled Above, and it very much links to the theme of today's presentation. It's a research topic focused on aerial observation of volcanic gas emissions, and it includes 20 researchers from 7 countries with a focus on the subduction zone in the vicinity of Papua New Guinea. And I think we will now be joining the talk. Thank you very much indeed.
Hello everyone, welcome to the talk today. My name is Emma Liu. I'm a volcanologist at University College London. My particular brand of volcanology is studying the gases that come out of volcanoes to try to understand something about what is happening deep beneath the surface. And today I'm going to be talking about how new drone technology is being used by the volcanological community to really change the way that we monitor volcanoes. This technology is game-changing. So volcanoes threaten people all over the world. Now, one of the examples you may have heard about is that of Vesuvius volcano. Now, Vesuvius is right next to the city of Naples that has a population of more than 2 million people. Now, if there was to be an eruption at Vesuvius in the modern day, this would represent a catastrophe on a huge scale. We know that to evacuate enough people from the hazard zone around Vesuvius would be almost logistically impossible. Now, this case study represents a fantastic example of situations that we're seeing all over the world where growing populations are forcing people to live closer and closer to active volcanoes. And in fact, the slopes of volcanoes often have very fertile soils, which actively encourages people to settle near them. Now, the other extreme, while Vesuvius is an explosive volcano, some volcanoes are known for their lava flows. This is Kilauea volcano in Hawaii, and in 2018 it had a devastating eruption where a series of fissures, you can see one in the photograph here, opened up within a residential district called the Lilani Estates. And this destroyed hundreds of homes and displaced hundreds of people from this residential district. But in the lifetime of the volcano, this is simply part of the volcanic life cycle. And if we look back in time at other lava flows on the island, this is a repeatable occurrence and another example of communities that choose to live within volcanic hazard zones. But it's not just within the Western world where we are living alongside volcanoes. This is a small tribal community in Papua New Guinea on an island called Manam. There is a population of around 4,000 people, and the island itself is a volcano and has, in the last 12 months, it's had 5 large eruptions, which have displaced the population to the mainland. However, part of their culture and their tradition is a strong tie to the island and the volcano, and it represents something very strong to them culturally. So they choose to return to the island and accept the risks posed by the volcano in order to live the lives they choose to lead. So as volcanologists, these three examples really highlight to us the other factors that need to go into volcano monitoring. We need to be sensitive to cultural factors when we are making recommendations and interpreting volcanic activity in terms of what communities may do in terms of mitigation measures or response measures. So the different types of volcanic hazards that we need to worry about are lava flows, volcanic gases, pyroclastic flows, and volcanic ashfall. So each pose very different risks. Now, pyroclastic flows are arguably the most devastating. These are superheated clouds of gas and ash which race down the sides of volcanoes and pretty much destroy everything in their path. However, they often only have a very small footprint around the volcano that they affect. Whereas on the other hand, we can consider volcanic ashfall. Now this may not be such a devastating hazard at first, but it acts by affecting infrastructure. If it lands on roofs and becomes wet, it can cause roofs to collapse. It poses a respiratory hazard. So it acts over much longer timescales, but over much wider areas. Ash can be transported hundreds of kilometers in the atmosphere, so affect communities living very far away from the volcano itself. Lava flows. We saw an example in Kilauea in Hawaii, where lava flows have caused huge damage to communities and infrastructure. They, depending on the properties of the lava flow, they can move very, very fast or very slowly. But it's, given past experiences, it's been very difficult for civil protection to attempt to divert lava flows. So often the best volcanologists can do is offer very high resolution predictions of where the lava flows are most likely to travel. And then finally, volcanic gases. This is probably the least well recognized of volcanic hazards. There are many volcanoes around the world that are passively reducing, emitting gases all the time, and we'll talk a little bit more about volcanic gases later in the talk. But these communities around these what we call open vent volcanoes are inhaling very low concentrations of these gases all the time. And so again, this can pose a very strong respiratory hazard, can contaminate water supplies and introduce toxic components like fluorine, fluoride into the water. So this is a digital product from the Smithsonian Institute, the National Museum of Natural History, and it shows volcanic eruptions and earthquakes all over the world through time. So this is a video that animates from around 2010 up to 2016, but you can very clearly see where volcanoes and earthquakes are located, along the boundaries of the Earth's tectonic plates. So convergent plate boundaries or subduction zones, such as what we see along the western coast of North and South America, are real concentrations of volcanic events as the new magma generated by subduction really feeds these chains of often quite explosive volcanoes. So some of the topics I'll be talking about today is an overview of how we monitor volcanoes, what parameters do we look for, then how are drones advancing our ability to monitor volcanoes. I will be drawing on two case studies, a volcano in Papua New Guinea, Manam, which you saw earlier in the talk, and then looking at how we monitor air quality in Hawaii during the effusive eruption in 2018. So broadly, these are the main ways that volcanologists employ to try and understand what is happening at a given volcano. So firstly, we can look at geodesy or ground deformation. If magma is intruding or entering into the volcanic system, then we would expect to see inflation of the volcanic edifice. This may only be a few centimeters, but we often use satellites to take measurements that can detect these centimeter scale inflations and deflation events. So this can be a really key parameter for flagging new potential sources of unrest. You can use thermal imaging. Now this is often more useful once an eruption is actually in progress, but is very effective for remote sensing lava flows and looking at the direction of lava flows given how much heat they are emitting. Seismology, or the study of earthquakes. This is a real cornerstone of volcano monitoring. And when a volcano first shows signs of unrest, installing a seismometer to measure the movement of the earth, the earthquakes, is one of the first things that we would attempt to do. It can give us the most information for the minimum infrastructure. So firstly, we would look for the amount of earthquakes, so the number of events. We can also look in more detail at the type of events, as different types of earthquake reflect different processes. We can have brittle failure earthquakes that represent cracking of rocks. So as magma is pushing its way towards the surface, we may expect it to be opening up cracks in the Earth's crust, and we would be able to identify this type of earthquake from the trace of a seismometer. We can look at gas emissions. So this involves taking a sample of the gases coming out of the vent at the top. And for volcano monitoring, the parameters we're most interested in is the emission rate of species such as sulfur dioxide. We may expect the emission rate to rise ahead of an eruption as the magma rises towards the surface and starts to exsolve more of the gases that have been dissolved in it. We can also look at changes in the chemical composition of the gas. I'll explain more about this as we go on, but crucially, the ratio of carbon dioxide to sulfur dioxide is used by volcanologists all over the world to understand things like the depth of magma stored beneath the volcano. More recently, we've started to use infrasound, or the acoustic study of noise from volcanoes. Now, infrasound is at a region of the acoustic spectrum outside of human hearing, so it's not something you'd be able to hear, but it's been very effective at picking up kind of the very early stages of eruptive activity from many distances away. And then finally, petrology, the study of previously erupted rocks to look at their geochemical composition. I've included this even though this is not a real-time measurement that we can take the measurement off and look at the result on the screen as it happens, but actually a lot of our understanding of what a volcano has done in the past helps us to understand what it may do in the future. So the study of petrology and the history of a volcano is crucial when we're assessing the hazard it poses. So how do we actually perform these measurements? Well, traditionally it's been done by direct sampling, where volcanologists would install an instrument often on the crater rim or somewhere very close to the source of the signal. Now this has the advantage of giving a very high resolution signal, but you can clearly see the hazard involved to the scientist in doing this. And arguably the most crucial time to have good quality data is when a volcano is showing lots of unrest or a strong sign of an eruption. But this is clearly not the time where we want to be anywhere near the crater rim. At the other end of the spectrum, we use remote sensing. Now, this can be from a ground-based instrument located several kilometers to tens of kilometers from the volcano, or from satellites in space. Remote sensing has proved an amazing technological revolution for looking at big picture global changes in volcanic activity. So for things like ground deformation, satellites are able to cover the entire surface of the Earth on a daily or weekly timescale, providing very high temporal resolution in order to flag new occurrences of unrest that we may not be able to identify on the ground. But crucially, for volcanic gases in particular, we can only measure sulfur dioxide, which is only one of many gases that volcanoes release. This is because sulfur dioxide is not present in the background atmosphere, and so it's very easily detectable even from space. But what the development is happening now is that drones are really bridging the gap between direct sampling and remote sensing. So they're allowing us to take measurements very close to the vent while we stay at a safe distance. So they are minimizing a lot of the sources of uncertainty involved in satellite remote sensing but at the same time adding a lot more flexibility and capability for us to increase the number of volcanoes around the world that are monitored. So the last few years have really been a UAS revolution. Now, UAS, unmanned aerial system or unoccupied aerial system, they're all different ways that you can refer to drone. So we can use either something called a fixed wing, which looks more like a traditional aircraft, or we can use a multi-rotor, which includes a series of propellers. Now, each of these I use in my research, and each of them has a very different application. So if we're looking to carry maybe a very heavy instrument and hover in one place for a long period of time, then we would choose a multi-rotor. This is very good at very precise positioning and can carry heavy loads. But for those volcanoes where we need to fly up to 10 kilometers away from us and very high altitude, then fixed wings are fantastic. They can cover much greater distances very quickly and remain in the air for up to an hour. But they can only carry very light sensors. So it's always a trade-off. You have to think about your application when choosing your vehicle. Now, drones are ideally suited to generating topographic models. So we can use a process called photogrammetry. This is where you take photos, hundreds of photos, at lots of different angles around an object of interest. And you can use these photos to generate a topographic model. And if you repeat this process over days or weeks or even years at a given volcano, then this has been shown to be really effective at modelling changes in the shape of the volcanic summit. So similar to what I described from satellites, where we can look for centimetre scale changes in the volcano shape that may indicate magma intrusion, we can use drones to perform a much higher resolution model over smaller areas. On the right hand side is a figure from the Kilauea eruption in 2018, where repeated drone surveys allowed us to model the collapse of the summit caldera over a period of several months. Aerial views are also excellent for modelling lava flow properties. So we can look at the velocity of lava flows. This is very effective in a crisis situation where we want to know how fast the flow is moving. So again, going back to Kilauea in Hawaii, the drones flew over the lava flows with a nadir camera looking downwards, and using a feature tracking algorithm, we could derive the flow velocity field from this imagery. We can also use the topographic models created by aerial imagery to predict the lava flow directions based on a model that uses the lines of steepest descent. And the greater the resolution, the spatial resolution of your topographic model, the more accurate your hazard map will be. So this was used in real time during a lava flow event in Hawaii, where this map was updated in real time in response to model runs every single day. So the local community was very aware of the dynamic hazard and how it changed through time. We can use drones for geophysical surveys. This is an excellent application. So we can cover much larger areas as we can fly higher. Often geophysical surveys are performed over areas of several square tens of kilometres, which would take days or weeks to perform a similar survey on foot. So in this way, we can create a much more instantaneous snapshot of the subsurface geology. This is an example here of a thermal survey, and on the right hand side we show a magnetic survey. Often magnetic surveys are very good for revealing subsurface geology, such as a buried magma body. We can also use them to collect samples of volcanic ash. So volcanic ash causes local regional impacts on health and infrastructure, but you may have also seen in the news about the impacts of ash on aviation. You may have even been impacted by the 2010 eruption of Eyjafjallajökull in Iceland. Now we're developing sampling mechanisms that can be mounted on fixed-wing aircraft and fly through the volcanic cloud in order to collect an in situ sample that we can bring back and analyse in the lab. These are microscope images magnified very strongly. This is about the size of a tip of a needle, but we can look at the size and the shape of ash particles to understand more about how they will behave and be transported in the atmosphere. And then finally, the subject of the rest of the talk. Drones are very good for measuring volcanic gas emissions. So we can use them to measure the emission rates of volcanic gases. We do this using something called a spectrometer. So the spectrometer measures incoming sunlight and how this sunlight is affected by passing through the volcanic plume. So we can traverse the spectrometer beneath the volcanic plume, looking upwards, and it will measure the absorption of sunlight by the gas species of interest, in this case sulfur dioxide. We can also use miniaturized sampling mechanisms to collect samples for gas chemistry measurements. And these can either be performed in real time, so the gas is sucked into the instrument, analysed and emitted in real time up in the air, or we can collect them in a sealed inert bag to bring back to perform isotopic analyses in the laboratory later on. So volcanoes release huge amounts of volcanic gases into the atmosphere, and the gas composition itself can tell us something about magma storage and ascent. The main gases released by volcanoes are water vapour, carbon dioxide and sulfur dioxide, although they can also release minor halogens like hydrogen chloride and hydrogen fluoride. So volcanic gases can be released in different ways. Probably the most well-known you'll have seen is explosive degassing. Now, both of these types of emissions pose very different hazards. Explosive degassing is very high intensity. It can inject gases right up into the stratosphere, which affects climate. But these are sporadic and transient events. Whereas passive degassing, these happen continuously, persistently at a low level. So the volcano is not actively erupting, but it is still emitting gases like a chimney. And these persistent low-level emissions can have a much greater effect on regional air quality and health of the communities living around the volcano. So this is a long-term hazard, whereas this is a short-term, very acute hazard. So explosive eruptions are driven by bubbles of gas that grow in the magma. Now this is a microscope image showing a cross-section through a pumice. This pumice was emitted during a very explosive volcanic eruption. So you can see it's full of bubbles, it's very porous. So gas is dissolved in magma at depth inside the earth. And this gas is only released when the magma starts to move towards the surface and loses pressure. It decompresses. It's like taking the lid off a Coke bottle. You'll see the Coke in the can, you'll take the lid off, and suddenly all these bubbles will nucleate and grow. And this is exactly what happens within a volcano. So just briefly, the theory behind why we can use gas emissions for monitoring is that the solubility of these different main gases is pressure dependent. And this varies for each gas type. So as I said, as the magma rises towards the surface, firstly CO2 will form bubbles. Then as the magma rises a little bit more and decompresses more, then sulfur dioxide will form bubbles. And then water, and then hydrogen chloride. And we know from experiments very clearly what the expected sequence of gases will be. So we can create models to explain what patterns we expect to see in surface gas emissions, so that when we go to a volcano showing unrest and we take our measurement, we can use this information to say something about how deep we think the magma is. And if we have a time series of measurements, we can actually track the ascent of magma towards the surface. Now, how can drones help with this? So probably the clearest advantage is that it's safer for the scientists. As a community, we're trying to work to make our science safer. From a scientific point of view, we can measure all types of volcanic gases. So because we are taking the measurement in situ and not using remote sensing, we can measure accurately what is present, even for species like carbon dioxide that have a very high concentration in the ambient background atmosphere. We can also measure much closer to the vent. So some of my work has shown that even over distances of a couple of hundred meters from the vent, so still very, very close, the volcanic plume can mix with the atmosphere, dilute, and undergo chemical reactions that will modify the gas chemistry from what it was when it was emitted from the magma. And what we want to know is that primary gas composition. So the closer we can measure, the better. And in a hazard situation, when an eruption is developing very quickly, drones can be deployed rapidly and at relatively low cost. So they represent a very versatile tool for monitoring. So this is our first case study, a volcano called Manam in Papua New Guinea. And in the last few years, I've been leading a project called Above, aerial-based observations of volcanic emissions. Now this is internationally collaborative, involves about 30 scientists from 9 different countries. And we've been working together to really develop drones for volcanic gas measurements. So this project has 3 main strands. There's been the technology development. We've been miniaturizing what would be 2 or 3 kilogram ground-based sensors. They're now a few hundred grams and we can fly them on drones. We're providing new insights into volcanic degassing. So we've been measuring the emission rates of carbon dioxide and sulfur dioxide from this volcano Manam in Papua New Guinea. And we've been engaging local communities and local researchers within the country to learn how to use this drone technology we've developed and continue the time series of measurements long after we've left the field. So this is how we create legacy in our project. So Papua New Guinea has very complex plate tectonics. I won't go into the detail, but there are a lot of small microplates all moving and jostling for position. So it's a very active region volcanically, and there are lots of volcanoes. The main ones here I've highlighted in orange, and Manam is shown by a star here. So Manam volcano had a very explosive climactic eruption in 2004, which caused the entire population, around 6,000 people at that time, to be evacuated to the mainland, where they stayed for almost 10 years. Now recently there's been renewed activity at Manam with 6 major eruptions in the past 18 months. And the main town or village on Manam is up in this northwest quadrant up here. And this is also the prevailing wind direction. So the fall of volcanic ash is a very strong hazard for this community because it destroys their crops and it contaminates their water supplies.
So this project is called Above, Aerial-Based Observations of Volcanic Emissions. This project all the way from the beginning has been about pushing boundaries of how we study volcanic emissions, changing the way we take our measurements, and how can we use the rapid advances in modern technology recently to help us get better data, fill in some of the gaps in our knowledge of volcanic emissions globally. Also how we can integrate lots of different techniques all happening at the same time.
Volcanoes are the main recycler of carbon from the mantle to the atmosphere. What we want to know is how much of the carbon that comes out of a volcano is from the mantle and how much is from the subduction zone. And by looking at the isotopes, we can do that. We can then make a balance and understand how much of that subducted carbon actually goes beyond the volcanoes down into the deep mantle. So it's an important part of understanding the global deep carbon cycle. A more practical aspect of the project is to understand what is the volcano doing. The more things we can measure, the better it is for us to understand why volcanoes erupt and when they erupt.
This is an instrument called a multigas. These have been deployed on many volcanoes around the world, and they play a really important role because changes in carbon dioxide and sulfur dioxide chemistry in the plume and the ratio between them can be used to forecast volcanic unrest.
So we put together this interdisciplinary team to develop sensors, sample collection systems, that we can put on drones and fly into volcanoes. The idea was to measure carbon dioxide as we fly through the plume and in real time get the data back to the drone operator. And then when the CO2 concentration is high enough, we trigger a little pump that then takes the gas from the plume and puts it into this plastic bag. Then we take the plastic bag and analyze it for carbon isotopes.
Oh,
here you go.
Volcanic gas straight from the crater of Tavuvu. We can already look at the concentration. So the ratio between those two tell us about the carbon isotope composition.
So this is a figure showing some of these long-range flights that we performed. So we would be flying 2 kilometers altitude up into the atmosphere and 7, 8 or 9 kilometers away from us horizontally. Now this was really pushing the boundaries of what is possible with current drone engineering. So this project really represented a interdisciplinary effort between aerospace engineers and volcanologists and earth scientists to be able to achieve these kind of measurements. So in all these figures, the drone path is shown and it's color coordinated according to sulfur dioxide concentration. So you can see as we passed over the summit, we measured very high concentrations of this sulfur dioxide. This is some of the views of the summit that we observed, and we could clearly see that there was a lava lake present within the volcanic crater. So we could call this volcano an open vent volcano, as it has a clear pathway to the magma surface and is passively releasing gases constantly at a very high rate. Now, what was on board the drone? So we used something called the multi-gas. Now this is a miniaturized gas analyzer that measures CO2, sulfur dioxide, hydrogen sulfide, and also meteorological variables like pressure, temperature, and relative humidity. And this is now about the size of a small sandwich box and weighs about 500 grams. We also carry one of these spectrometer systems that I mentioned that measures the absorption of sunlight, and this quantifies SO2. We also have an onboard gas collection system where we can use small pumps to collect physical samples of the volcanic gases to bring back. And using these bags, we can perform more complex geochemical analyses, like looking at carbon isotope compositions. This is an example of the fixed wing aircraft that we used. It has a wingspan of about 2 meters, so it's very large. And this is an example of a multi-rotor.
Working in a country like Papua New Guinea, it's never going to be easy in terms of particularly logistics and just working in the field. But that's part of the reason why no ground-based measurements existed, because it's been extremely challenging.
What we've got to remember is this is a remote island with no gas, electricity, water. So everything we're doing here is using the most basic facilities available to us. So we've bought tools, we've bought battery chargers. Charging is always the challenge, I think, on a trip like this. So many drones need so many batteries.
2 different kinds of drone batteries charged, 5 computers, and we have 2 car batteries as well. We have some chaotic thing over here, but it works.
All the drones, all the different types of instruments. I mean, everybody's working hard making it happen, but it's, you know, it's very, very ambitious.
We're trying to push the boundaries, and when you push the boundaries, things will go wrong. It's challenging for the people who work here, it's challenging for the instruments. We've had instruments fail because of the heat.
Well, we were about to take off, but the computer shut down. It looks like it overheated, so the sun is really making a toll on the instruments.
Once I had to put it in the freezer for a couple of minutes and then it worked again.
At 34 degrees.
Okay. No way, that's too hot.
People have been working really hard to push the vehicles beyond their design capability. The sheer magnitude of the volcano, that sort of 2,000 metre climb, that's not something that most drones are designed to do. So getting all the way to the plume is definitely a challenge.
Oh! You're down. That's a crash.
Why is it so bad?
Now?
Battery.
Oh.
Yeah.
So when we're flying in volcanic plumes, there is a lot of technical and environmental challenges that make it very difficult. So this is just an example of some of the different challenges that we face. Now, wind is a real problem. There are often very strong topographic winds around volcanoes, which make it very difficult to fly. We also cannot use combustion engines, which would greatly improve the endurance or the time that we could spend in the air. But crucially, the exhaust fumes for combustion engines have a very similar gas chemistry to some of the gases that are released by volcanoes and we're trying to measure. So it would contaminate our samples. Acidity is also a real problem. So there's a lot of water present in the volcanic plume and also a lot of sulfur dioxide. And when you mix sulfur and water, you create sulfuric acid. And this will corrode any metal or electronic components on the drone. I often get asked about temperature. So how can the drone withstand the temperatures above volcanic vents? Well, actually, the temperature of volcanic gas can decrease extremely quickly above the surface of the vent as it mixes with the atmosphere and entrains cold air from the surroundings. So actually, even when the drone flies very close to the top of the volcano, it's only a few degrees above ambient. We measured as part of this study the G-force that a drone experiences as it flies through this turbulent plume above Manam volcano. And we saw that actually it experiences vertical accelerations of up to 25 meters per second. And this acceleration translates to about 2.5 G-forces. So for a lightweight foam aircraft, this is quite substantial. So we'll be using a lot of this information to improve the design of future drones. Now we know exactly what kind of forces it will have to withstand in the future.
The first challenge is the launch. So it's a hand launch. It's this moment when the vehicle goes to full thrust and you have to throw it into the sky, and then the autopilot takes over at that moment. And it's a very critical moment because the autopilot has to get the wings level, has to continue ascending, but shortly after that moment everything becomes a little bit calmer, the thrust backs off, the autopilot's doing its job and starts navigating to the waypoints. Yep, off it goes. This is good. When it goes into the turn, can you tell me what it recovers to? We set it at maybe a 13-degree climb angle, and it powers up in several large zigzag tracks just back and forth into clean air until we reach 2,300 meters above sea level. Once we're at that, we fly directly towards the plume and we turn back. Yep. Okay, if it's 22.8, I am a go. Fantastic news. Ready?
Titan has landed successfully in parachute mode.
Disarm, please.
Please disarm and confirm.
The SO2 value is a very clear indicator that we've hit the densest part of the plume. It's a great feeling, and then when they came over and said we nailed it, we hit the plume, we were right through the middle, couldn't have been happier.
We got there eventually.
So from this campaign, we derived some really useful scientific information that feeds into our global data set of volcanic gas emissions, as this volcano was a real known unknown until these measurements. So we found we're releasing almost 4,000 tons per day of CO2. Now this is an enormous carbon flux. But another important part of this project was the community engagement aspect. Now we held a workshop, a training workshop for volcanological staff and local scientists to train them in how to fly drones and incorporate these kind of strategies into their hazard monitoring and response efforts. So now this is Kilauea, this is the lead volcanologist in Papua New Guinea, and he now regularly flies aerial monitoring flights to collect volcanic gas data from Rabaul volcano. So hopefully this time series will continue and really help to increase resilience to natural hazards in Papua New Guinea. So our second case study is looking at the 2018 Kilauea eruption in Hawaii. Now this eruption, most of the lava was emitted from a fissure called Fissure 8. This is a map of the lava flow over the entire duration of the eruption. So Fissure 8 is where the lava came from, and it travelled downslope all the way to the ocean entry. So this is a photograph taken from a helicopter showing the effect of the eruption on the regional air quality. Now you can clearly see the gases being released, and then this diffuse region, a hazy region beneath the cloud, is what we call aerosols. So these are very, very fine particulates of volcanic ash, of small sulfate particles, basically things that you really wouldn't want to be breathing in. If we look on the right hand side, this is a comparative figure looking in the same direction during the eruption and then a year following the eruption. You can see the difference in the air quality at ground level. It's very hazy up here and it's very clear after the eruption. So we went out there because we were concerned about the overall air quality for the big island of Hawaii and how the volcanic plume was being transported around the island. So we used a combination of ground-based and drone-based measurements to characterize what was being emitted at source. So the drones would be able to fly directly over Fissure 8. As I said, we could calculate the speed of the lava flows, but we were interested in collecting physical samples of the volcanic gases to know really what was coming out at source. We then used a series of ground-based measurements located in a network all over the island of Hawaii to then track the movement of sulfur and metal particles all the way around the island. So this is a figure of what we found. So this is Fissure 8 over on the right hand side, and this is a model showing how sulfur moves around the island and also how it transforms chemically from sulfur dioxide gas to sulfate aerosol particle, which can be breathed in. So you can see that over a time scale, this plume is 17 hours old by the time it reaches the town of Kona. And by that time, about 20% of the gas is converted to sulfate aerosol. So actually the air quality over in Kona was exceeding environmental air quality thresholds. So the recommendation was that people had to remain inside, even though they were across the other side of the island from the eruption itself. Now I won't go into every aspect of this figure because it's fairly in depth, but these are some of the trace elements that we were measuring in the plume. So volcanoes release metals like copper, zinc and lead in tiny, tiny particles. And as the plume gets older and it moves further away from source, these metal metals particles are deposited out of the plume. And what we were interested in is, what is the timescale which this happens? And can we use our sampling network to create a hazard map of likely exposures for people living in different parts of the island of Hawaii? But crucially, none of these models work unless you know the source composition in order to initiate your models. And drone-based approaches allowed us to collect that information in what was otherwise a very hazardous area to enter. So what's next? What's the future? So I've just embarked on a new project where we are looking at drone deployable sensor pods. So we want to build up an array of low power, lightweight sensors, also very low cost, so we can translate them into developing countries, that we can deploy using drones around volcanic craters to measure heterogeneity in gas emissions within a volcanic crater itself. And we would like to integrate these with satellite communications so that they can provide a remote monitoring tool for monitoring organisations like in Papua New Guinea to get a really good idea of what is happening at the volcanoes. So this is what's next for me over the coming 12 months. So to summarise what we've talked about, the way we monitor volcanoes is changing. It's becoming much more flexible and drawing a lot more on new developments in technology. Increasingly, we can use drones or aerial approaches to make all kinds of measurements that we'd normally make on the ground or from space. And importantly, using aerial approaches are minimising a lot of the sources of either hazard or measurement uncertainty in either our ground or space-based approaches. So these strategies hold many advantages for the future of volcanic hazard assessment, and what we really aim to do is over the next 2 to 3 years is translate what we found to something that volcano observatories can use in an operational capacity. So we can have a tangible effect on helping to mitigate the risk posed to communities around the world by volcanic eruptions. And I'm happy to take any questions that you may have, either about drone-based strategies or volcanology more generally. Thank you.
Hello, Emma. I hope you can hear me.
Hi, yes, I'm here.
Oh, excellent. That's good to know. I don't want to be speaking into a vacuum. That was an extremely informative and very engaging presentation, and fantastic use of electronic media. People have been commenting on that in the background. And, you know, that really kind of sums up the professionalism of the projects that you've been undertaking as well. Just to inform the rest of the audience, you can insert questions into the Q&A function at the bottom of your screens if you want to. We already have some questions there. So a couple of questions. I don't know whether you can see these as well, Emma, but how many drones do you lose to volcanoes has been asked. And also, I'll give you this one as well. Do volcanoes around the world emit gases in different chemical proportions? And I think you've partly answered that, but do easterly volcanoes emit less sulfur than west, for example?
I can definitely summarise that again for everyone. So yes, we do see a difference in chemical proportions in the gases being released by volcanoes in different parts of the world. And this is controlled mainly by tectonic setting. So rather than a geographical control, it's determined by what's causing the volcano to be there in the first place. So we would expect very different chemistries for, say, a volcano erupting in Iceland, which is along a mid-ocean ridge, compared to a volcano along an arc setting, like we would see along the western coast of South America. And that's largely due to magmatic processes deep beneath the crust. So beneath arc volcanoes, we're having subduction. So a plate is subducting beneath a continental plate. And this is supplying what we call volatiles, which ultimately become volcanic gases, into the magma source region that the volcano taps.
And we also see variations between different types of arc volcano, depending on what sediments are being dragged down into the subduction zone. So if we're taking carbonate sediments down into the trench, then we would expect very carbon dioxide rich volcanic emissions. There's also a shallow control on chemistry. So although we have an overall composition that's set deep in the mantle, we can also use relative changes in chemical composition as a forecasting tool. So for a given volcano, we can say if the carbon to sulfur ratio changes in a pattern we would expect, then we can track the ascent of magma towards the surface. So I guess, yes, that summarizes my answer to your question.
That was a superb answer, just as clear as your presentation. Thank you very much indeed. There are a couple more questions now, and I'm going to start with the bottom one, which asks, in the Papua New Guinea volcano, the magma was at the surface. So what change in CO2 and SO2 ratios would you expect to get an explosive eruption?
Yes, very interesting. So yeah, we could see magma at the surface. So it is what we call an open vent volcano. So it's essentially being a gas pipe and emitting gas all the time. However, when magma is sitting at low pressure, so near the surface, the most stable gas to be released is sulfur dioxide. So if we were expecting a new input of magma from below, which may signal a new explosive eruption is imminent, as has been seen at other volcanoes like Stromboli and Etna, then we would expect the carbon to sulfur ratio to spike towards high CO2 compositions. As carbon dioxide exhaled to form bubbles and gas bubbles at high pressure. So we can actually use the change from to high carbon to sulfur ratios to say, okay, a new batch of magma has entered at depth. And then if this gradually then evolves over several days, maybe up to weeks, towards lower carbon to sulfur ratios, then this, in combination with other monitoring tools like earthquakes, we can actually track the ascent of magma towards the surface. We would also expect a change in the overall magnitude of emissions. So as well as changing chemistry, we would expect the volume of gas to be released to also increase.
Goodness me, that's excellent. Thank you very much indeed. And I'm actually going over to the chat, which means that there's actually a contribution from the panelists. Also thanking you very much indeed for the fantastic talk. But asking the question, can you explain how you prevent aerosols from damaging your equipment?
So aerosol particles, and these can include either volcanic ash particles or small sulfates or chlorides particles. You're quite right, in the aviation engines, this can be extremely damaging. It's the same situation in drone-based measurements, in that we try very hard not to fly within ash-rich plumes. So where there's a lot of volcanic ash, then our propeller blades will also be vulnerable the same way as aviation engines. However, they're not quite as vulnerable in the fact that they operate at much lower temperatures than typical commercial aircraft. So we will have a problem from abrasion and from particles actually blocking the turbines, but we won't have the same problem of the ash particles actually reaching their melting point and solidifying against the turbine blades, which is the most hazardous component of ash to commercial aviation engines. So there's we both use avoidance, but also the time we spend in the plume is usually much less, so our exposure is low. And a lot of cleaning of the drones when they come back to ground.
Yes, I can imagine that. Thank you. You're doing amazingly well, because this is quite a broad range of questions. Finally, I'm going to ask what programming languages and software development tools do you use for the sensors and the analysis?
Okay, so most of the analysis of the gas data that I do is done either in Python or MATLAB, very commonly used as programming languages within science. So there's nothing specific that we use. The digital data that comes in is in the form of a large spreadsheet and time series that we can analyze the same as if it would be geochemical data from petrology or other measurements.
In terms of actually developing the sensors themselves, I work closely with the engineers who you saw in the video, and they use programming languages like Arduino. We program small Raspberry Pis to run some of the sensors. Mostly we're using open source programming languages that are open to the whole scientific community.
Thank you very much indeed. And we are closing the session there just a couple of minutes ahead so that we can arrange the next presentation. But on behalf of us all, Emma, that was a really superb presentation. You covered such a breadth of input, from the impacts on people through to the technologies and the geological background. You obviously understand a lot about gases and their decompression ratios. A really, really interesting presentation. I'm sure we've all learned from that. Thank you very much indeed.
Thank you so much for so many people joining in to listen this morning. I realize it's early on a Saturday, so thank you all for your time as well.
Thank you. Bye-bye.
Bye, have a good day.
Yeah, and you.